Here we're going to dive more into ideal gases as we discuss gas laws and the ideal gas law. First, though, I'm going to just give a brief overview of what ideal gases are. So, if you ever done anything in physics where you talked about using frictionless surfaces and massless strings and stuff like that, we kind of create this ideal situation in physics where the math is simpler, and you can learn and gain a lot of intuition, and develop understanding of relationships, and then you can kind of add in the non-perfectness later. That's kind of what we're doing here. We're going to talk about gas laws. So let's talk about what an ideal gas is. An ideal gas is just this idealized way that we treat gases as if they behave this way. Now, it's not a bad assumption. There's a lot of gases that behave very ideally, but nothing behaves perfectly ideally, but it's pretty good. So let's talk about, there's 5 things that a gas needs to be ideal. The first is it needs no, the whole thing, intermolecular forces. Now we'll talk about intermolecular forces in a later video, problem set 26. But basically all this means is that when the gas particles run into each other, they don't stick to each other, they don't feel attracted to each other, they treat each other as platonic billiard balls, so to speak. Alright, no intermolecular forces. Now this order doesn't matter, but another assumption is that the gas particles are in constant random motion. 3, that collisions are all elastic. Now what that means is that kinetic energy is conserved. So if you think of a car accident, 2 cars are driving, they have kinetic energy, they run into each other, and they stop moving. That is not elastic, because kinetic energy is not conserved. But billiard balls, if I hit the cue ball, it's moving very fast, has a lot of kinetic energy, it hits a different ball. Even if the cue ball stops moving, all of the kinetic energy essentially is absorbed into that second ball, and so that is an elastic collision. And gas particles, ideal gas particles, behave elastically. Okay, number 4 is that the volume of particles is pretty much 0 compared to the space they take up. Okay, because gases spread out so much that the actual particles themselves, their volume is negligible. And lastly, we just say that kinetic energy is proportional to temperature, which we talked about a little bit on the problem set 23. All right, so these are the assumptions. You need these 5 things to say that a gas is ideal. Now, we're never going to expect you to say, oh, I got to figure out if this is ideal or not. We don't expect you to do that. We do expect you to understand these concepts. That brings us to question number 1. Which of the following are not characteristics of an ideal gas? So, the first one says the molecules have little volume compared to the volume they occupy. Literally wrote that. Volume of particles is pretty much 0 compared to the space they occupy. So, that one is a characteristic of an ideal gas, and therefore is not an answer here. The volume is independent of temperature. That is not true. We'll talk about later, but when you heat up a gas, it expands. Think of a hot air balloon. That's what allows hot air balloons to float. Heat up a gas, it expands. So the volume is not independent of temperature. All right, C, the density of all ideal gases is the same. That's also not true, and we'll get to talk about that one, particularly. Is it on this one? Yeah, it is. Nope, that's on problem set 25, but we'll get to talk about that one a lot. And then gas atoms or molecules do not interact with one another. That's what this first assumption is. There's no intermolecular forces, so no interactions there. All right, what would happen to the pressure of ideal gas under each of the following conditions? Well, before we can answer this question, we need to talk about the ideal gas law. I mentioned that as you increase the temperature, the volume of a gas increases. We have this relationship between temperature and volume. Well, if I increase the temperature, the gas particles move faster, moves faster, generating more pressure as well. So we have a relationship between temperature and pressure. We know that if we add more moles to a balloon, the balloon gets bigger. Blowing air into a balloon makes the balloon bigger, so we have a relationship between moles and volume. So there's all these different relationships between parameters for a gas. But for an ideal gas, they collapse into this beautifully simple equation. PV equals nRT, meaning pressure times volume equals moles times the ideal gas constant times temperature. Now for this class, usually pressure we'll have in atmospheres, volume we'll have in liters, N we'll have in moles, and temperature we'll have in Kelvin. As a result, we need to use the R value that has units of liter atmospheres over moles Kelvin. And that is 0.08206. We used 8.314 when we were doing root mean square velocities on problem set 23, but that was in units of joules per mole Kelvin. That's not the units for this equation, so we don't want that, we want this guy. Alright, so let's look at how to solve these problems. What would happen to the pressure if each of these things happened? Well, I know that pressure is going to be nRT over V. I just took this equation divided by V. Anything I do to the right-hand side of the equation, I've got to do to the left-hand side of the equation. So I'm going to double volume, keeping everything else constant. Well, if I'm doubling volume, I'm multiplying this whole thing by 1/2, so my pressure needs to get multiplied by 1/2. Does that make sense? We're going to do some more of these. I've got pressure equals nRT over V. I reduce the temperature to 1/3 its original value. So I take the temperature, I multiply it by 1/3. That'll give me 1/3 of the temperature. If I multiply this side of the equation by 1/3, I've got to multiply this side of the equation by 1/3. Okay, quadruple the number of moles, multiply that by 4, while keeping the volume and temperature constant. Well, if I multiply this side by 4, that side needs to be multiplied by 4. I double the volume, double the number of moles, keeping the temperature constant. Well, now I'm multiplying by 2 and dividing by 2, so nothing's going to happen to the pressure. And then I reduce the temperature by 1/3 and double the volume. Double the volume. If I reduce the temperature by 1/3, do I multiply the temperature by 1/3? No, because the temperature started off as 3/3 or just whatever it was. 3/3 is just 1. If I reduce it by 1/3, now it's going to be 2/3. Okay, so I've got a 2/3 multiplying by 2/3 and dividing by 2. That means multiplying by 2/6 or 1/3. Now this next one, quadrupling the number of moles, decreasing the volume by 1/2, so to 1/2 its original value, and reducing the temperature to 3/4 its original value. So I've got a 4 on top, I've got a 3/4 on top. Dividing by 1/2 is the same as multiplying by 2. Those cancel, and then that's left with 6. So I'm going to get 6 times the pressure. Hopefully that way of answering those questions works out. And that brings us to, oh, come on, there we go. Brings us to number 3. Number 3, sorry, give me a second. There you go. On a cold winter night, you discover that your thermometer is broken, and you decide to use a knowledge of gas laws to determine the outside temperature. In your warm 75-degree house, you fill a balloon with an ideal gas to a diameter of 1.56 feet. You place the balloon outside until it equilibrates with the cold. You measure the new diameter to be 1.51 feet. What is the temperature outside? Okay. Treat the balloon as a sphere with that volume to radius relationship. Okay, so this is, there are two ways that we really use the ideal gas law. One way is to be given, right, we got 4 variables here. One way is to be given 3 of the variables, and then we just use the law to find the 4th. A different way, though, is what's going on here, and that's when we have a gas in condition, I'm going to say condition 1, and it moves to condition 2. We know some things that change. We want to find the other things that change. This is the way I like to set these up. I know that for any gas, PV over NT equals R. Just divide by N and T. That's true for any gas. So if that's true for gas 1, that's PV over NT is also going to be equal to R for gas 2. So if this is P1 V1 over N1 T1, this is P2 V2 over N2 T2. Because they're both equal to R, they're equal to each other. Then I can look at this equation. So this is where I start always when I have a gas changing from situation 1 to situation 2. Anything that doesn't change during my transition is the same on both sides of the equation, and therefore I can just erase it. And the other things we can fill in. So let's look here. We know we have a gas changing from one set of conditions to another. All right, so what changes? Well, we know the temperature changes. We go from 75 and we're trying to find the second temperature. We know the diameter changes, and diameter is associated with volume. So we know temperature and volume are going to change. That means, because they don't say anything about pressure, pressure doesn't change. Because they don't say anything about moles, right? It's just a balloon, it's a closed space, moles aren't going to change. So we get this relationship of V1 over T1 equals V2 over T2. Now this relationship has some name. It's named after some really old dude, but you don't need to know the name as long as you can get there from this PV over NT equals PV over NT. All right, we also know, I'm going to simplify this even more. We also know that volume equals 4/3 pi r squared, pi r cubed. I'm going to replace this volume with 4/3 pi, and r is diameter over 2 cubed. That's diameter 1. This one's also 4/3 pi, diameter 2 over 2 cubed. And what's cool about this? 4/3 pi is on both sides of the equation, therefore can be canceled. Okay, so now I have this even more simplified equation. Okay, but both of these, this could be written as d1 cubed over 2 cubed and d2 cubed over 2 cubed. Well, both of them have 2 cubed, and so that can cancel as well. So really what we get is d1 cubed over t1 equals d2 cubed over t2. Now, you could just use the two diameters and calculate volumes, okay, but this just simplifies and gets rid of some of the steps. Oh, goodness. All right, so let's do this now. I know that D1 is 1.56 feet. I'm going to do that. And T1 is 75 degrees Fahrenheit. But I can't put Fahrenheit here. Temperature has to be Kelvin. My other parameters, whenever I'm doing this situation 1, situation 2 problem, I can use whatever units I want as long as they're the same on both sides, because there's no R value in these equations defining my units. I can't do that for temperature, though, and it's because when we convert temperatures, we're using addition, and so the math doesn't work out that simply. But let's convert the 75 degrees to Kelvin. So we're going to first change it to Celsius. We do that by subtracting 32 degrees, or 32, and then we multiply by 5/9. That gives us our Celsius, but we want Kelvin, so then I'm going to add 273. Yay, that gives me a temperature of 297 Kelvin. That's going to be equal to D2 squared. D2 is 1.51 cubed over T2, which means I can now solve for T2. I get T2 is 269 Kelvin. Let's get that to Celsius. Gives me negative 3.6 degrees Celsius. And if I want to get that to Fahrenheit, I take 3.6, I multiply by 9/5, and I add 32. and that gives me temperature outside is about 25.4 degrees Fahrenheit. All right, so this again was situation 1, moving to situation 2. Let's do a couple more of these. How many? Down to 7. Okay. Spherical weather balloon has a diameter of 3.5 feet, temperature 78 degrees Fahrenheit. Inside the Arctic Weather Station, temperature is negative 35 degrees Fahrenheit outside. What will the diameter of the weather balloon in feet be? All right, we've already got this equation set up. Remember, this is a PV over NT, PV over NT, but we simplify pressure and moles aren't changing, and then we replaced volume with the D1 cubed relationship. So I've got 3.5 feet cubed. All right, 78 minus 32 times 5/9 plus 273. Got me see, that gives me 299. Then my second temperature is negative 35. That gives me what did I get? 236 Kelvin. I solve for D2. And I get 3.23 feet. If the balloon is released and rises to an altitude where the pressure is 100 torr, what will be, and temperature stays the same, what will be the diameter? All right, so taking a gas, changing its conditions. Okay, what's changing? Well, the pressure is changing from atmospheric pressure, 1 atmosphere, to 100 torr. Okay, and the temperature's not changing, so the temperature's still the same. And the moles aren't changing. So then we get P1 V1 equals P2 V2. All right, so P1 is 1 atmosphere, which is 760 torr. V1, it wants diameters, okay? So remember, instead of V, we can use D cubed. So I'm going to replace this with D1 cubed, D2 cubed. So what was D1? Well, this is after the change, right, because the temperature is 35. So after the change, this diameter was 3.23 cubed equals pressure 2 is 100 torr, and we're looking for D2 cubed. And I get D2 equals 6.35 feet. That's my new diameter. The world record for diving without supplemental air tanks is about 125 meters. The depth at which the pressure is 12.5 atmospheres. Divers along the volume is 6 liters at the surface. That's their volume at that depth. All right, so PV over NT equals PV over NT. Pressure's 12.5. So pressure's changing. And it talks about volume, so volume's changing. So we get another P over PV equals PV. Pressure at the top is going to be 1 atmosphere because that's just at the surface of the ocean. Volume at the top is 6 liters. Pressure at the bottom is 12.5 atmospheres. I'm looking for V2. And I get that V2 equals 0.48 liters. Bicycle racer inflates his tires to 7.5 1 atmospheres on a warm autumn afternoon when temperatures reach 25 degrees C. We talk about pressure, we talk about temperature. Temperature changes, what happens to the pressure? What's changing here? We got pressures and temperatures involved. So volume isn't changing, volume's the same, and moles isn't changing because our tires aren't releasing anything. So we get P1 over T1 equals P2 over T2. Pressure first is 7.1. Temperature is 27 plus 273 gives me 300. Temperature changes to 5, so 278. What's the new pressure? I get a pressure of about 6.6 atmospheres. And the last question, suppose atmospheric temperature and pressure at the top of a ski run are -5 degrees Celsius. So we got our temperature 1 and our pressure 1. At the bottom we get our temperature 2 and our pressure 2. How many more moles of oxygen does a skier take in with a lung full of air at the bottom of the run than at the top? Express it as a percentage. So in this case we're not looking for N1, we're not looking for N2, we're looking for N2 over N1. It's going to give us what percent of N1 do you get at N2. So P1V1 over N1T1 equals P2V2 for N2T2. And we say the volume of your lungs isn't changing. We just have pressure, temperature, and moles. And we're trying to get N2 over N1. So how do I rearrange this? I want N2 on top over N1 on bottom. And I already have P2 here and T2 here. I got to multiply T1 over and divide P1 over. Well, pressure 2 is 734 millimeters mercury. Temperature 1 is -5 degrees Celsius, which is 268. T2 is 273. And P1 is 713. And I get that N2 over N1 equals 1.01, which means N2 equals 101% of N1. So if you could get 100 molecules in your lungs and at the top, then you could get 101 molecules in your lungs at the bottom because of the increase in pressure. Okay, so here we introduced the ideal gas law and the assumptions of ideal gases, and we learned how to use the ideal gas law. There's 2 real ways. You can use 3 variables to find the 4th, or you can do a situation A, situation B type problem.